Howdy, this is the Amateur Logician. This video we're going to be starting Chapter 2 as we work our way through the textbook First Course in Mathematical Logic. This video covers Section 2.1, Introduction, and part of Section 2.2, Rules of Inference. This is on propositional logic, and in this video we will be covering modus ponens, two-step proofs, double negation, and modus tollens. The next video will be dealing with things like the law of conjunction, simplification, the disjunctive syllogism. Let's get started. Let's take a look at the introduction. Remember that the logical form of a sentence is determined by its sentential connectives, such as the and, the or, the not, the if-then. Here's what's new. The rules of inference allow us to arrive at new sentences. We can call these conclusions given previous sentences, which we can call premises. This process of using premises and the deductive rules of inference to arrive at a conclusion is a deduction. And for our purposes, at least, we can use the following words as more or less interchangeable. The Suppes and Hill textbook uses them as more or less interchangeable. Derived, inferred, deduced, proved. To be sure, these words might technically take on slightly different connotations, so they're not exactly equivalent, but for our purposes, we'll treat them as more or less equivalent. This is really the heart of logic. It's about inference. If we're given some premises, we could then, so to speak, try to pull out of those premises new things. We can try to derive various conclusions. And one of the rules of inference is modus ponens. We can simply call this modus ponens for short. And in fact, most textbooks simply call this rule of inference modus ponens, and so will I. We can abbreviate this as MP. And here there are two given premises. The first major premise is a conditional. P implies Q, or in other words, if P then Q. The second premise is P, that is, it asserts that P in fact is the case, and with those two premises we're able to derive something new, that therefore Q is the case. Those three dots mean therefore. It's important to recognize that the major premise is just a conditional. It's a hypothetical. It's nothing else but that. It's saying if P is the case, then Q is the case. It's not asserting that P in fact is the case. It may or may not be. Likewise, it doesn't tell us that Q in fact is the case. It might be, it might not be. So in other words, the conditional is only telling us that P, the antecedent, is sufficient for the consequent Q. So P is sufficient for Q. This means if we're just given the premise if P then Q, there's no way we can conclude that Q is the case. Obviously that would be fallacious. But if we also know, in addition to that first premise, that P is the case, then of course we can get this conclusion because P is sufficient for Q. Here's an example from the textbook, page 44. We're told if it is raining, then the sky must be cloudy. It's a conditional. It is raining is the antecedent, P. The sky must be cloudy is the consequent, Q. So it is raining is sufficient for the sky being cloudy. Second premise, we're told that it is raining, and so therefore the sky must be cloudy. If P, then Q, P, therefore Q. This very simple exercise is just to make sure we understand what's going on. We want to derive a conclusion. We want to prove a conclusion from each of the following sets of premises. For example, number 1, we're given two premises. The first premise, if P or Q, then R. Second premise, P or Q. P or Q assert something is the case, either P or Q, and so we can assert that the antecedent in fact is the case, and thereby we could assert that R is the case. Thus, through modus ponens, we can derive R. And likewise, for example, with sentence 2, we're given the premise, if not P, then not Q. We're given the premise not P, so we're able to get not Q by modus ponens. Because not P is being asserted to be, in fact, the case, we can say that antecedent is true, and that's sufficient for not Q being true. Likewise, for number 4, we have if P, then Q and R. Second premise, P P affirms that antecedent, so we can get that consequent, Q and R. So it's as simple as that. I suppose I rushed through that a little bit, but I do want to think about proofs here. So here is our simple modus ponens proof. And what we do is the following. In a proof, we will number each and every sentence. Sentence 1, sentence 2, sentence 3, etc. Then we have the sentence, if R then S, R, S. We then have a justification. For example, sentence 1 is P, sentence 2 is P. P stands for premise. And a premise is simply a given sentence. We take it for granted. Sentence 3 happens to be MP. Its justification is that we derived that sentence with sentence 1, sentence 2. MP stands for modus ponens. Most textbooks use the abbreviation MP. The Suppes and Hill textbook, interestingly enough, uses the abbreviation PP for modus poendo ponens. But for our case, I'll stick with MP because that's the standard convention in the vast majority of contemporary textbooks. A proof can have 2 steps, it can have 3 steps, it can have 100 steps. So here's an example. Let's say we're given 3 sentences. These are our premises. So this is sentence 1, sentence 2, sentence 3. We have if A, then B. We have if B, then C, A. This is a premise, this is a premise, this is a premise. We can then derive sentence 4, B. And we have to justify this. This is modus ponens, and we use sentence 1 and sentence 3. So we have sentence 3. It affirms that A, in fact, is the case, and that appears as the antecedent to a conditional. We could affirm that antecedent, and then we can affirm that consequent. So that gives us B. The important thing is we number our sentences, and we also have to justify our sentences. So this is modus ponens, but I have to specify what sentences were used in that inference. So we use sentence 1 and sentence 3 to derive B. For sentence 5, we can get C by modus ponens with sentences 2 and 4. Because sentence 2, we have the conditional if B, then C. Sentence 4, we know B is in fact the case, so we could affirm the antecedent for sentence 2 and then affirm the consequent. And this allows us to derive that consequent. We can derive C. The point is, in a proof, we always list our sentences, we number them in ascending order. We also have to justify each and every sentence. It could be a premise, or we might have derived it through some inference. And if it's an inference, we have to say what specific sentences we used in that inference. Part C of exercise 3 on page 52, we will do 2 problems, number 2 and number 3. Number 2, we want to prove B given a list of premises. Notice that line 6, we have a conditional if M then B. B does appear as the consequent to that conditional, but there's no way we can just, so to speak, pull that B out. What should be our strategy here? I think we should look for a statement that declares itself categorically to be the case, or not to be the case. So line 3, we are told that G is not the case, so this is a declarative absolute statement. It's not a conditional. It's saying this is the case. It is a fact that G is not the case. And that does appear on line 1 in the antecedent to a conditional, so we could affirm that antecedent, and that is sufficient for us to affirm that consequent E. So for line 7, we can derive E by the modus ponens inference with lines 1 and 3. Note that we first numbered our sentence. This is sentence 7. We have the sentence E, and we have to justify it. We got it through the modus ponens inference using lines 1 and 3. Now that we know that E in fact is the case, notice line 2, E appears as the antecedent to a conditional. So E is a case, we could affirm the antecedent, and so we could affirm that consequent to get K. Hence for line 8, we can get K by modus ponens with lines 2 and 7. We have K, that is the case, and it just happens that K is the antecedent to another conditional on line 4. We could affirm the antecedent to affirm that consequent, and so it follows that not L is the case by modus ponens with lines 4 and 8. Once again, we have not L, and it just happens that not L appears in a conditional, it's the antecedent. We could affirm that's the case, and so that's sufficient to say that M is the case. So for 10, we can say M by modus ponens with lines 5 and 9. But if M is the case, we can look at line 6. It's the antecedent. And so we can get that consequent B. So for line 11, it therefore follows that B is the case by modus ponens with lines 6 and 10. And that concludes that proof. For number 3, we want to prove the disjunction R or S. So once again, I think the best thing to do is to look for something that declared to be absolutely the case. And we have that. We know for a fact, because it's a given premise on line 1, that C or D is the case. So either C or D is the case. That's a fact. But because that is a fact, we could affirm the antecedent to line 2 to get not F. So for line 5, we can get not F by modus ponens with lines 1 and 2. Not F appears in line 3. We could affirm the antecedent to get that consequent. Thus for line 6, we can get A and not B, modus ponens, lines 2 and 5. And that also allows us to do another modus ponens inference, because line 4, we have A and not B, but we know that's a fact, and that's sufficient to say that R or S is the case. Hence for line 7, therefore, R or S by modus ponens with lines 4 and 6. It's as simple as that. We make sure we list the numbers of the sentences, and we have to justify them. Each step, each inference we have to justify. Another very important type of inference is double negation. In fact, we can call this an immediate inference, in that this type of rule of inference allows us to take any sentence whatsoever and immediately infer another. We can double negate any sentence to get another sentence. Double negation is abbreviated as DN. Here's an example from the textbook on page 52. It is not the case that Anne is not a student. Note that we have two negations. It's a molecular sentence overall. We have the atomic sentence, Anne is a student. And let's abbreviate that as A. But we're told that Anne is not a student right here. So we have to have a negation there, not A. Anne is not a student. But then we have, it is not the case that Anne is not a student. So we need another negation. Hence we have not A. What does that mean? Well, obviously it means that therefore Anne is a student. In other words, we have arrived at the conclusion A. So from not A, we get A. Two negatives, so to speak, yield a positive. Or we might say, with two negatives, one cancels out the other one. Let's take a look at these premises and conclusions. So clearly, premise 2, we have not Q. That's the same exact form as this not A. And obviously from not Q, we can get a Q. That's the conclusion. Similarly, if we think about the first premise, P, we can get not P. In other words, we could say that P is the same thing as, or it's equivalent to, not P. From this left-hand side P, you can arrive at this right-hand side, not P. Or the other way around. From this right-hand side, not P, you can arrive at this left-hand side, P. That's why they're equivalent. That's also what makes, in a way, double negation an immediate inference. We can immediately pull something out of one single sentence to get another sentence. The exercise on page 53 just wants us to double negate these sentences. Sentence 1 tells us that all mammals are warm-blooded animals. How would we double negate it? We would just have to say it's not the case that all mammals are not warm-blooded animals. So it's not the case that all mammals are not warm-blooded animals. So that is our new sentence, but it's really equivalent to our original sentence. It has the same meaning underlining it, because W is equivalent to not W. These three bars means equivalent to. So W is equivalent to not W. What about sentence 2? It is not the case that the nucleus of the atom is not positively charged. So we have really here not C. Well, in this case, we are moving from something that has two negations, and those negations just cancel each other out, so we're back at something that is, so to speak, positively affirmed. In other words, the nucleus of the atom is positively charged. And of course, if we took this sentence and double negated it, we would return back to our original sentence. The last rule of inference for this video will be modus tollens, or simply modus tollens for short. And modus tollens we will abbreviate as MT. Now when considering modus tollens, tollendo means denying the consequent, and tollens means denying the antecedent. Like modus ponens, we start with the major premise, if P, then Q. The second premise states Q is not the case, and from that, we derive the conclusion, not P. We can abbreviate this either as MT or TT. The textbook uses TT for tollendo tollens. We will not. In these videos, we'll just use the standard convention of MT. But also note that when considering the major premise, if P then Q, it is a hypothetical, it is a conditional. Note that the consequent Q is necessary for the antecedent. In other words, for P. Q is necessary for P. So this means that given premise 2, that Q is not the case, it must mean that P is not the case. So that conclusion is valid. It's based on this understanding that Q is necessary for P. Here's an example on page 52 of the Suppes textbook. If it shines by its own light, then the heavenly object is a star. It shines by its own light. It's the antecedent, P. The heavenly object is a star is the consequent, Q. Second premise, the heavenly object is not a star. We're denying that consequent, but that consequent is necessary for the antecedent, hence we get the conclusion, therefore, it does not shine by its own light. And that makes intuitive sense. Just consider modus ponens. So if you have first premise P implies Q, P, the conclusion is Q, right? So if P is the case, Q would have to be the case. So it makes sense that if you have if P then Q, not Q, therefore not P. Because if Q is not the case, there's no way in the world P could be the case. Because if P were the case, you would have Q, but Q isn't the case. So how could P be? So therefore modus tollens makes a lot of sense. So we have these two major rules of inference for our mixed hypothetical syllogisms. We have modus ponens and we have modus tollens. Those are the only two valid forms of the mixed hypothetical syllogism. As we wrap up this video, let's do 3 more proofs. This is from part C of exercise 5 on pages 57 to 58. Number 1, we want to prove C given 3 premises. We have the premise not B, we have the premise if A then B, we have the premise if not A then C. We are told that it is categorically the case that not B. And so, because we do know that, we can look at sentence 2 and we see the consequent in a conditional. which is B. So we're denying that consequent, and so we can deny the antecedent through modus tollens. Hence, for line 4, we can say not A by modus tollens with lines 1 and 2. Because we can deny B, and B is necessary for A, we can deny A. But since we now know that not A is the case, we can look to line 3. We could affirm the antecedent to that conditional to derive C by modus ponens. So for line 5, therefore it does follow C by modus ponens with lines 3 and 4. And that concludes that proof. For number 3, we want to prove R and S. It's a conjunction, and we're given 3 premises. Premise 2, Q is declared to be the case, so that's a good starting point. Does Q show up anywhere else? Well, it does in premise 1. We have this not Q. But this is very important because Q and not Q contradict each other. So in a sense, Q is denying this consequent. So we can thereby deny the antecedent. But before we can do that, we have to make this explicitly clear through double negation. This is a very, very important step. So for line 4, we can get not Q by double negation of sentence 2. So this is an important step here. We're immediately inferring from line 2 not Q. But not Q denies explicitly not Q. We have not Q, and if we have a not, these are, we're negating it. We're saying, hey, that's not the case. And so we can deny the antecedent. So for line 5, we get not P by modus tollens with lines 1 and 4. But since we know that not P is the case, we could affirm the antecedent on that conditional, line 3, to get the consequent R and S. And so for line 6, therefore, R and S by modus ponens, lines 3 and 5. And that concludes that proof. For number 5, we want to prove not S. Is anything declared categorically to be the case? Well, certainly. We have R on line 2 as a premise, and R denies not R, but we want to make that explicitly clear. So for line 3, we'll say not R, and that's just by the double negation of line 2. So we have this not R, and this negation here denies that. And this means we are denying, in fact, or we can deny that consequent to that conditional. And so for line 4, it therefore does follow not S by modus tollens with lines 1 and 3. And that concludes that proof. All right, I think this is a good place to stop. Up next, we will finish up section 2.2. Thank you for watching.